Whether my audio is clear?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So what we are discussing is estimation of viscosity. So in that, whatever material I have taken is from this Birds Towards and Lightfoot. This is the book actually. So this book I am using majorly. Okay. So this is written by Bird, Stewarts and Lightfoot and commonly called as a BSL, Transport Phenomena by BSL. So if you go in this book, so whatever we have covered, it is given also this viscosity and you can say Newton's law of viscosity, generalized Newton's law of viscosity, and then we have moved to actually heat transfer coefficient, which is covered in interface flux actually here. So it is not given in chapter 1. So I followed another book, but in this book also that information is given. Okay, in this book also that information is given. That is here you can say. So interface flux. So if you go here, so you can say definition of friction factor for flow around that sphere, friction factor for packed bed. So this already we have covered. So kind of I'm simultaneously this covering chapter number 1 and chapter number 6. This is for momentum transfer. Similarly, if you go in this book, so you can see thermal conductivity. You can see chapter number 9. So Fourier law of heat conduction. Okay, this we have covered. And here also we have a interface flux. So chapter number 14. Chapter number 14, okay, definition of heat transfer coefficient. And so we have not covered in detail. This force convection and all is not there in your syllabus because this is not purely that you will be covering some part of this chapter in advanced transport phenomena. We are sticking ourselves to steady state, laminar flow, and simple mathematics. We are not going in complicated mathematics in short. So whatever we can understand simply using complete differential equation, partial differential equation is not used. That part only we are covering. So analytical calculation for this heat transfer coefficient, some of this thing is there. So similarly for mass transfer, you can see here. So mass transfer, diffusivity and all, fixed law of diffusion. Okay. So and then here interface flux. Okay. So definition of mass transfer coefficient and analytical expression for mass transfer coefficient. So if you go in this book actually BSL, this is very good book. I just request everybody to purchase this book if possible. So Eastern Economical Edition is available. So that is not very costly also. So it can be you can buy I think within 700 or so. Okay, cost of this book. So currently what we are looking for is chapter content from chapter number 1 and then contents from chapter number 6. Okay, contents from chapter number 1 6 and then energy transport chapter number 9 and then chapter number 14. Okay, chapter number 1. So this 1 6 chapter number 9 14, and then in mass transfer, okay, it is chapter number 17. Okay, 17, and interface flux is there in this actually this chapter number 22. Okay, this is what we are covering, but for this I have not followed this book till now. I have followed some other book, but content is there in this book also, but only in some other language. So you can say chapter number 1 6 9 14 17 and 22, this is there in this book. But what I am following is this book actually, Modeling in Transport Phenomena. This is written by Ismail Tashan. Okay, he has compiled same thing he has compiled but in simpler language. So Ismail Tashan. So this Modeling in Transport Phenomena, it is by Elsewhere Science and Technology. So if you go in this book, so this is what I have covered. Chapter number 1, okay, content wise actually I have covered actually this molecular and this, okay, here also same thing. So this chapter number 1, I have not covered that much. Actually, chapter number 2, from here we have started Newton's law of viscosity, then Fick's law of diffusion, then Fourier law of heat conduction. As it is, I have covered. Okay, as it is, I have covered from this book. So if you refer, and I think everybody might having a soft copy of these two books. So roll number 88.
Yes,
Roll
sir.
number 88 is there in it. Yeah.
Yes, sir. Hello.
Pratish, whether you have soft copy of these two books,
Uh, yes, sir.
both the books you have, na? So you
Yes,
can circulate, but this will be unofficial. Okay, don't circulate.
yes, sir.
Don't make it official because there will be copyright issue. So hence I cannot give this book. I can use this book for teaching. That's all. So as it is, you circulate in a class because this I got from student only both the copy. I was struggling to get this Ismail Tashan book. In 2010, some student gave me this book. So likewise, you are much more clever than me, getting all these books and all. So this you can, and better. I will suggest at least you buy this transport phenomena BSL. One book you should have hard copy also. So don't rely on soft copy all the time. So at least one subject, this transport phenomena BSL will cover heat transfer, mass transfer, momentum transfer. You should have that book. Okay, this I have covered actually chapter number 2. So where molecular flux is discussed, convective flux is discussed, total flux is discussed, dimensionless numbers are discussed. Then I have moved on to chapter number 3, transfer coefficient. Okay, interface flux actually. So here we have discussed uh, Heining equation, then we have discussed Newton's law of cooling, and then we have discussed Slattery equation, okay, and physical interpretation of these all these equation, heat transfer coefficient, mass transfer coefficient, and dimensionless number. Then we have discussed this evaluation of transfer coefficient. So I have just discussed 4.1, and this already this flow over flat spheres. Other point you can study on your own because this is just a put the values and get the answer. Actually, that is what is there. So, and in last class, what we have covered, that is also same thing actually, but there is some theory involved in this. For that only, I am discussing everything. This is what we have covered in last class: pressure and temperature dependence of viscosity. So this is the empirical graph. Okay. So even though it looks so simple, what is the graph? So it is mu by mu c plotted against T by Tc for different value of P by Pc. So reduced temperature is plotted reduced viscosity. This is reduced viscosity is plotted against reduced temperature at different reduced pressure. Even though this graph looks so simple, these you will find so many empirical graphs in your different study: heat transfer, mass transfer, thermodynamics also. But for getting this graph, you can see here itself. You can say almost 100 year of engineering is there in this one graph. So here itself it is mentioned. Okay, K.M. Watson has given first time in 1994 and revised by again K.M. Watson in 1996. Again Roger and K.M. Watson again revised in this graph in 1960. Okay, so you can see whenever you are getting this empirical graph, how these empirical graphs are obtained. These are the compilation of all the experimental observation and proposed model by different researcher over the year. This is not the work of only, this is just a compilation. K.M. Watson has compiled all the data. It is not everything is done by K.M. Watson. If you go the details of this reference 1960 K.M. Watson, you will see list of the paper. There will be thousands of paper involved in getting this empirical graph. Okay, and this is experimental data and some partial whatever be the model proposed by different researcher is compiled together, so that you can have a short compilation of information in the form of pictorial representation of all the data. That is what called as an empirical graph. And in last class we have seen, so here we have temperature by critical temperature, you have pressure by critical pressure, and here you have viscosity by critical viscosity. Out of this, say six parameter, say five parameter is given, so you can estimate six one. Certainly this critical temperature will be given, this is property of the material. Critical pressure is given, this is again property of the material. Using this critical temperature and critical pressure, you can estimate critical viscosity. So three property you can get it from data book. Okay, and precisely in this BSL, if you go to appendix also, you should know how to use this book also. So that is what I am showing this book actually. So if you go in this appendix, okay, so you can say this appendix, all these appendix, this is all data is given. So if you go in appendix E and this intermolecular forces and all, so here you can see for hydrogen, critical temperature is given, critical pressure is given, critical volume is given, critical viscosity is given, critical conductivity is given. Okay, so everything is given here actually for hydrogen. Okay, hydrogen. So most important point to know is, okay, so most of the time you will make a mistake that here temperature is given in Kelvin, because other all the properties, so there will be multiplication factor for conversion, but in temperature there is a actually addition is there. So if you reduce this temperature in Kelvin by degree Celsius, you will get altogether different answer. Okay, and whatever this data, it is in angstrom, it is in atmosphere, and then you should use this in this unit, and that will be given along with this thing actually. So these are the, you can say, potential parameters and critical properties. Okay, so all data is compiled, and this kind of data you will get from different books also. It all depends upon which book is explaining which engineering correlation in which way. So you can say here hydrogen, helium, this thing, everything is there. Hydrocarbons are there. So you can say other organic compounds also is there. Okay, and these are all references they have given. So this doesn't mean that only these many compounds will have these properties, because these are the important compound as per as this BSL thought that this data will be used for transport phenomena book. Hence, he has given only this much information. Otherwise, you can get the information from each and every compound. So using this data book, so you can get, here you can see critical temperature, you can get critical pressure, you can get critical viscosity also you can get. And there is another alternate way also, another alternate way where you can get this critical viscosity. Where is that? Uh, so this already we have discussed. This empirical, you can say, empirical relation using critical pressure and critical temperature, you can get an empirical viscosity also. So out of this six parameter, three parameter you can get it from data book. Now remaining is temperature, pressure, and viscosity. So out of this three parameter, if two parameter is given, so you should be able to estimate the third parameter. This is what the you can use this empirical graph. Then we have seen this actually molecular theory of viscosity of gases. You can say from kinetic theory, you can get this. This is, I think, velocity, average velocity, or this is frequency and everything. And they have discussed this two molecule force of interaction, negligible, and everything. And they have derived this equation. They have derived this equation. If somebody is more interested, so it needs actually statistical thermodynamic information, hence I am not going in details in this. Only the as far as transport phenomena point of view concerned, this equation is important for us. So this equation, so it has some theoretical background for deriving this from kinetic theory of gases. So here you can see somewhere it might be written actually. So we consider a pure gas rigid, non-attracting spherical molecule of diameter dm. This is assumption. Okay, this is assumption which gives me this equation, and this equation we have used. Okay, here nothing is needed actually. This diameter is needed. Okay, and this molecular mass is needed, and this is Boltzmann constant, and this is temperature. So you can get the value of viscosity. Okay, this expression is obtained by Maxwell in 1860. Okay, and then actually here they have modified. Okay, then actually this new area. Okay, where people have used statistical thermodynamics and use high calculating computers, high computation and statistical thermodynamics. Then comes the area molecular dynamics simulation. Okay, so from first principle, Newton's law of attraction and all, they have derived using this statistical thermodynamics and molecular dynamics simulation. They have derived this equation. Okay, this is also given by I think Maxwell only. So and this Lennard-Jones potential. This is the term which you got from molecular dynamics simulation. I think some of you might be doing a project in this molecular dynamics simulation with Professor Vanjari might be knowing this actually Lennard-Jones potential. Then this is collision diameter and this is collision integral. Okay, so again here also our main aim is to use this equation. Will not go in derivations, but there is some equation which is derived theoretically, which will give me a viscosity of gases. This is specifically for viscosity of gases, monoatomic gases, and it can be used for polyatomic gases. This equation can be used for polyatomic gases also. Again, these are the some of the important information which is available in you can say data books. Actually, if you go in data books, actually, again I think it is there in this only. Here you can see actually this is called as a collision diameter, and then using collision diameter and temperature you can get the value of epsilon by kt. Okay, you can see epsilon by kt or kt by epsilon. Okay, epsilon. Okay, this again epsilon, what is epsilon is, so here somewhere it might be mentioned. Okay, this epsilon by k is also one of the parameter. Okay, this is again that Avogadro's number, and epsilon is some emissivity kind of thing actually. So this epsilon by k is there, temperature is there, so you can get the value of kt by epsilon. For different value of kt by epsilon, you can get a, this is collision integral. This is collision integral for viscosity and thermal conductivity. This is the collision integral for diffusivity, and you can use this data to get this value of viscosity actually, to get this value of viscosity. So that is what we are going to see. So derivation of these equations are not our main aim actually. Our main aim is just to have a feel that there are some equations available. There are some equations available which will give me a viscosity if needed. So because viscosity now, hope you got the feel that viscosity is one of the most important parameter, thermodynamic property in momentum transfer or fluid mechanics. Viscosity, friction factor, and velocity profile. You will cover almost 90% of the design problem in fluid mechanics. Okay, if you have knowledge about viscosity, you have knowledge about friction factor, and you have knowledge about velocity profile, almost 90% of the problem in fluid mechanics can be covered. Design problem can be solved. So viscosity is very, very important, and this is one of the way we can get this viscosity. So this already we have seen, this is the Maxwell equation. So Maxwell equation, so where they have used this molecular dynamics fundamental. Molecular dynamics fundamental means nothing but the statistical thermodynamics, and large number of computation is used to get various properties. You can predict the various properties also from first principle. First principle, using first principle. So this is collision diameter, epsilon is collision diameter, and this is actually collision integral. So collision diameter is in angstrom, temperature is in Kelvin, viscosity is in gram centimeter per second, using this equation actually. And this molecular weight, actually molecular weight of the material. So preliminary Maxwell equation, that also which is for low density gases, where they have neglected the interacting forces between two molecular atoms. That and this Maxwell equation, advanced Maxwell equation you can call, which is derived from a statistical thermodynamics information. So both indicates viscosity is inversely proportional to temperature for gases. This is the most important take home message from both the equation: preliminary Maxwell equation, which is derived from kinetic theory of gases, and advanced Maxwell equation, which is derived from statistical mechanical information and molecular dynamics simulation. Both are indicating viscosity is directly proportional to under root of temperature. This many times you can use actually. If say you are not able to get the viscosity of water at say 75, water anyway, water is kind of liquid which is used very well everywhere. So if you are not getting say viscosity of some oil, so you have designed some synthetic oil for cooling and all, and you want viscosity of that oil. Say you are not getting a data from anywhere else. So certainly you can do the experiment. You can do the experiment, and again oil. Again, I am giving a wrong answer. This is true for only gases. Anyway, for take home message: viscosity is directly proportional to under root of temperature. Then we have solved this one problem. So where viscosity is directly proportional to temperature. So and as I told that, okay, this problem was asked in one gate also long time back. How many people have given a gate yesterday? How many people have? You can write in chat box. How many people have given a gate? Pritesh, nobody has given a gate from your class.
Given, sir. Many of them are given.
Okay, okay, okay. Now people are writing. Okay. Roll number 11, Chetan.
Yes, sir.
Whether there was any question asked from this transport phenomena which we have covered till now?
Yes, sir. One question was there.
What was that? Can you just elaborate on that?
Sir, there was one pipe in which there was another pipe which was moving with the velocity.
Uh-huh.
So they had asked the expression for the force. Uh,
And what
means
was the distance between this inner pipe and outer pipe?
Sir, means the inner pipe was of radius AR.
Mm-hmm.
Outer pipe was of radius
Ah,
capital R. Capital R.
and ask for laminar flow only.
Yes, sir.
Okay. Then I think because we have covered similar problem for flow over fat plate actually, flow between two plates.
Yes, sir.
So only the difference is now here and there is they have changed the coordinates. Okay, instead of Cartesian coordinate system, they have used a cylindrical coordinate system. But
And
whether you was able to solve that problem?
yes, sir. I had solved, but don't know it was correct or wrong.
Yeah, because uh, you now you just remind your name and roll number at the end when we will be covering how to get the velocity profile. Okay, how to get the velocity profile, shell balance approach. That time, once we covered that, certainly this problem is very easy to solve. Okay.
Okay.
Now also you can solve, but only the thing is slight additional information is needed, which we are going to cover. Anything else? This was for 1 mark only.
I think 2 marks, sir.
Oh, 2 marks. Very good. So anything else from gate? Anybody else remember anything you come across related to say basic fundamental uh, which we have discussed of transport phenomena till now? Anybody else?
Yes, sir. There was one question in which they had asked, like they have given two situations, and that two situation were giving two diffusion fluxes, and we needed to take the ratio of that two diffusion fluxes. That's all.
Okay, diffusivity is directly proportional to temperature raised to 2 by 3.
No, sir, it was not dependent on temperature. It was dependent on size, I think.
Oh, size of the molecule. So maybe same discussion what we are going now. So this, so I will show the equations for that also. Okay, how what is the temperature and pressure dependency of molecules? Size of the molecule they are given. Okay, they are actually this collision integral and this thing actually. So that depends upon size also. So that relation is also there. Okay, so that was for 1 mark.
Yes, sir.
Okay. So I think certainly there will be say approximate 5 marks question will be there from transport phenomena every year. So this is one of the question asked long time back. Actually, viscosity it is similar actually that there they have asked diffusivity. It is viscosity given at temperature one temperature and pressure and another temperature viscosity is asked. So this is this thing actually, and this is compute the viscosity. Okay, so even if no viscosity is given, this Maxwell advanced equation I will call it as this is also Maxwell equation advanced equation which has a background of statistical thermodynamics and molecular dynamics simulation. So I can use this equation. Okay. So provided I should have this collision diameter and collision integral. So collision diameter, as I shown you, so using this E point 1 Lennard-Jones potential parameters and critical property. This is called as a Lennard-Jones potential parameters. Okay, this is collision diameter and this is say Lennard-Jones parameter. You can call it as a. So using this E 1.1, so I will get this epsilon sigma. Sigma is a Lennard-Jones collision diameter. Collision diameter. So here we are looking for carbon dioxide. For carbon dioxide, sigma is 3.996 angstrom. Okay, and this critical property is not needed actually. Here, critical property is not needed. So this I can get from the table E.1. Okay, so E.1. Now what I want is I want this collision integral. So how to get the collision integral? I will get this is Lennard-Jones parameter. Okay, this I will this for carbon dioxide is 190, and for given temperature, so 200 Kelvin. At 200 Kelvin, what is the value of kT by epsilon? KT by epsilon. So this 200 divided by 190. So I will get the kT by epsilon value at 190 Kelvin. That is 200 divided by 190. It will be something around 1.1. So I will get this collision integral at 1.1. Similarly, at 300 Kelvin, 300 divided by 190. So it will be something around 1.5. So something here. So this epsilon by kT and 800 Kelvin. So I will get something around 4.5 or so. So using this collision diameter and collision integral, I can substitute the information in this equation 2.6693 into 10 raised to minus 5 under root of mt epsilon square by sigma m I can get the viscosity at 200 Kelvin, 300 Kelvin, and 800 Kelvin. So even though I am showing this table, this is actually broken table. Okay, this table is not in this form actually. This table is not this E to E point 2 is not in this form. Only 0.9 to 1.5 and 1.4. So it, let me see that. Is open. Yeah, it is open. So yeah, you can see. So I have broken this table. I have given only this information. So epsilon kt by epsilon is starting from point 0.3. It is given continuous up to 100. Okay, so you can get different value of collision diameter and collision integral for different value of kt by epsilon. So I have broken this as per our requirement, whatever be the needed. So using this two table, first of all, these Lennard-Jones parameters. So this is collision diameter and epsilon by k Lennard-Jones parameters, you can say parameter one. So and using this data, so and this collision diameter and collision integral, so you can get the viscosity of all these compound. You can say here, helium, hydrogen, neon, argon, krypton, xenon, air, nitrogen, oxygen, carbon dioxide, carbon monoxide, sulfur dioxide, then freon, chlorine, bromine, iodine, and these all are hydrocarbons, benzene, and all. So these other organic compounds also, and more. You can see this is the compilation of not all the information available in literature. This is the compilation of information which you need. Okay, so whether you will be able to solve this problem, compute the viscosity of carbon dioxide at 200 Kelvin, 300 Kelvin, and 800 Kelvin using Maxwell equation. Okay, just try to solve this problem. Everything is given, all data is given on this slide using my Maxwell equation. So Maxwell equation tells me that mu is 2.6693 into 10 raised to minus 5 under root. This under root is only to denominator, under root of mt epsilon square by mu m. So and this collision diameter is in angstrom, temperature is in Kelvin, viscosity will get in gram centimeter per second, and this is molecular mass per mole. Okay, so everything is given. Roll number 26, Vijay Babu. Roll number 26, Vijay Babu. Roll number 43, Akash.
Yes, sir.
Yeah, can you just give me an input how to solve this problem? Give the values. Already I told you actually.
Yes, sir. At 200 Kelvin, the
First,
value.
you should start with the collision diameter.
Yes, sir.
Uh-huh. So what is the collision diameter? Which collision diameter you are using?
For CO2, sigma
Okay, what is the
3.996,
very good. And what is the molecular weight you are using?
44
44. Very good. And then how to get a collision integral?
by using the E by K, epsilon by K
So what is the
for
epsilon by K for carbon dioxide?
190
190, 190, yeah. And then
divided by 200.
divided by 200. So what is the value you are getting?
1.05.
1.05. So exactly 1.05 you are getting.
1.053.
Okay. So now you can say it is given for 1.05, it is given for 1, it is given from 1.10. So you can interpolate this data for your 1.053 also, or you can get this. Now it is very close to 1.05, na? So you can use
Yes,
this.
sir.
What will be the value of your collision integral?
1.554.
Okay, so what will be the value of viscosity at 200 Kelvin?
1.009 into 10 raised to power minus 4.
That's all.
एक gram per centimeter second.
Very good. So units are very, very important.
Yes, sir.
Your roll number 1, Abhinav.
Sir.
Yeah. So what is for 300 Kelvin? Just repeat all the data first of all.
Uh, Sir, collision diameter will be same. That is 3.996.
Very good.
Then for KT by epsilon, we will divide 300 by 190. That is 1.57. So
Yeah, 1.57 now. Here you can see. So 1.57 data is not given. Okay.
we will take 1.55.
1.55 is given, 1.60 is given. So either you can interpolate linearly between these two data. Okay.
Okay.
So, or you can use any of the data 1.55 or 1.56. Accordingly, you will be getting the error. But I will suggest that you should interpolate the data. So if at 1.55, what is collision diameter, collision integral?
1.297.
At 1.6, what will be the collision integral?
1.280.
280. So what will be the value at 1.57?
So interpolation.
What everybody is getting what I mean to say by interpolation? You get this linear interpolation. You get the slope of the line and get the value at 1.57. So Abhinav, what is the value at 1.57?
Can-
Can you be little quick, Abhinav?
Uh, s- uh, yes, 1 minute. Sir, it is 1.2698.
It is wrong actually. It should be between 1.29 and 1.28, 297 and 1.280. It should be between this. 26, how can you get? So this is what the basic mathematical skill you should have. Before you should call as an engineer, you should have this basic this thing. Here, roll number 6, Aksh.
Yes, sir.
What
The
is the
same.
value at 1.57 collision integral?
So it's 1.286.
Yeah, that seems to be correct. Okay, that seems to be correct. Because just I'm I'm looking at these two values. I'm looking at 1.297 and I am looking at 1.28. If I want a value in between, certainly this value will be in between these two values. Okay. Now you can use this, and what will be the viscosity, Aksh?
Sir, the viscosity will be, sir, just a minute, I'm telling.
I request everybody again, you should sit with pen, paper, pen, notebook, and calculator in all classes of transport phenomena. You take these online classes as similar as offline classes. Only the thing is, I am sitting in my room, you are sitting in your room, and we are discussing. That's all. That is the only difference for online classes. If you take it this much seriously that as you are taking in offline classes, then there is no difference between online and offline classes.
Sir, it's 1.49 approximately. 1.49 into 10 to the power minus 4.
Yeah, that's all.
1.49 into 10 to the power minus 4 gram per centimeter second.
Very good. You should not miss the unit. Yeah, roll number 30, money. Roll number 30, money.
Sir,
Oh, why you are late? You are already in my list now. Okay.
sir,
Okay, why you are late? Late for answering.
I'm just turning on my mic, sir.
Oh, very good. So what is the viscosity at 800 Kelvin?
Wait a minute.
Hmm?
Calculating, sir. Wait a minute. Just around 3.2 into 10 power minus 4.
Yeah,
Around
money.
3. Sir, around 3.2 into 10 power minus 4 gram per centimeter into second.
Okay, what is the value of collision diameter you have used?
Sir, 3.960.
And what is the value of kT by epsilon you got?
KD by epsilon is 4.21, sir. 4.21.
4.21.
211.
211. So what is the value of collision integral?
0. 0.9594 around 0.9594, sorry, 0.9594.
Okay. And viscosity is? So, okay.
3.2.
Okay, everybody got this? How to get this value? Just check whether you are getting. For 200 Kelvin, okay, this is for 200, so you can this thing actually, so you this is in tabular form, so you just match up all this data at 200 Kelvin. This is epsilon by kT by epsilon 1.053, and this is collision integral. This is under root of temperature, and this is the value of viscosity in gram centimeter. This is predicted by Maxwell equation, and you can see this is observed value. Okay, so close. Experimentally calculated value of carbon dioxide at 200 Kelvin. So close. Experimentally calculated value of observed. Okay, this is taken from. You can go in that book, and this is taken from reference number 11. Okay, now. Hope you will be able to get the viscosity of all these gases. All these gases means at least whatever data given in this data book. Okay, all the data. So all the gases at all temperature and pressure. All temperature and pressure. So all temperature means this kT by epsilon starting from 0.3 to 100. So you should be able to get this viscosity value for all the gases. Now, once I have this viscosity of gases, so certainly I can get the how to get the viscosity of gas mixture. Either you can use that information which we have used in first actually. So you can get a viscosity and this just this here this equation I can use. This is very simple equation. Okay, where molecular interaction are neglected. Molecular interaction between say nitrogen and oxygen is similar to molecular interaction between nitrogen and carbon dioxide. If I have mixture of nitrogen, oxygen and carbon dioxide, I am neglecting a difference of interaction between nitrogen and oxygen and nitrogen and carbon dioxide. Okay, all are interacting equally. So if that is considered, using this is also empirical summation formula only. Okay, so where this interaction, okay, this dimensional concept, this is the interacting parameter between alpha and beta. So it is related with a molecular mass of alpha and beta and viscosity of alpha and beta. Okay, molecular mass of alpha and beta and viscosity of alpha and beta. Using this I can get this interacting parameter. Using this interacting parameter I can get the mixture of viscosity. Okay, viscosity. So this is the mole fraction of that component and this is the viscosity of individual component. This is mole fraction of say component, this is viscosity of the component, this is mole fraction into interacting parameter alpha beta. Okay, so using this empirical formula I can get the viscosity of mixture more accurately, because in first slide also I have seen that I can get a viscosity of mixture just neglecting this. So this is taken equals to 1, this is taken equals to 1. So what was assumed there? So say I have mixture of gases, all gases are interacting similar to each other. So interaction between say this thing actually, this again you can say same example is there, carbon dioxide, nitrogen and oxygen, oxygen and nitrogen. So oxygen is interacting with carbon dioxide, nitrogen is interacting with carbon dioxide and oxygen is interacting with nitrogen. If I take this all three interactions same, then I can get a viscosity simply this multiplied by this plus this multiplied by this plus this multiplied by this. I can get the viscosity of mixture. But if these are interacting differently, this is interacting parameter is there. If this interacting parameter is 1, so that value will exactly match. But this will give you more correct answer, because certainly oxygen and nitrogen will not have same interaction as that of oxygen and carbon dioxide and nitrogen and carbon dioxide. It will have different. So get me the value of this. Okay, using this mixture actually. So I will just briefly give you how to solve this. Okay, get this value. Okay, so this is actually beta and ratio of molecular masses, ratio of viscosity, and there is interacting parameter and summation of this interacting parameter. Then sum it up and then use this equation. Okay, use this equation to get the value of mixture. So this alpha varies from 1 to 3 and beta also varies from 1 to 3. 1, 1 indicates carbon dioxide, 2 indicates oxygen and 3 indicates nitrogen. So alpha varies from 1 to 3 and beta varies from 1 to 3. So I will get this ratio of, this is molecular mass. So get the ratio of molecular mass mu alpha by mu beta, mu alpha by beta. Alpha equals to 1 means carbon dioxide, alpha equals to 1 means carbon dioxide. Certainly you will have 1 here, 1 here. Okay, similarly you will have here 1, here 1. This will be also equals to 1. Okay, and this will be also 2 2 will be equals to 1, 3 3 will be equals to 1 1 1. So this ratio will be 1, and you substitute in this equation, you get the interacting parameter. This interacting parameter you got, you get this term. Okay, summation of x beta. So this again mole fraction multiplied by interacting parameter. you get this term, substitute in this equation. So you can see this is the molecular mass, this is the molecular mass, ratio of molecular mass. This 44 divided by 44, 44 divided by 32, and 44 divided by 28. Similarly, this is the ratio of viscosity. So this is viscosity, this is viscosity, uh, this is the ratio of viscosity. And now substitute this here in this equation, substitute in this equation. So I will get this quantity. Now mole fraction, okay, these are the mole fraction. So this multiplied by this plus this multiplied by this plus this multiplied by this, summation of this mole fraction into interacting parameter will give me this integral value. Okay, this integral value, this is equals to 0.763. If I neglect the interaction, this will be equals to 1. Okay, this will be equals to 1. So that is what this is there. Similarly, you can get this for, this is beta varies from, this is for alpha equals to 1. You get it for alpha equals to 2, alpha equals to 3. Okay, alpha equals to 2, alpha equals to 3, and sum it over here. So what will be the value here? So get me the value here.
0.727.
0.727 first value. Who is it?
Shubham Ranga.
Roll number?
91. Bit
19?
19. 91.
91. Just let me see. 91. Yeah. You are not written name. What is your name?
Shubham Ranga, sir.
Shubham. So what is the value here? 21?
0.27.
0.27. What is the value here?
Second value 1. Third value 1.142.
1.142. Okay, mu alpha by, yeah. And then what is the value? Viscosity, alpha by beta. Alpha equals to oxygen. Okay, alpha equals to oxygen and beta equals to carbon dioxide. First here.
For carbon dioxide, it is 1.389. And for O2, it is 1. And for En2, it is 1.158.
Okay, so what is the interacting parameter then? Phi alpha beta.
CO2 interacting parameter is 1.394. For O2 it is 1, and for N2 it is 1.006.
So what is the summation of this term actually? Mole fraction in
1.57.
how much? 0.57.
1.057.
Okay, 1.057. So you got that BSL soft copy. You are reading from BSL soft copy or you are calculating?
Reading, sir.
So that is not the thing, na? I am asking
Okay.
you to do the calculation and let me know.
Right, sir. Cross checking also.
Okay.
So getting same value or not.
So you have calculated 1.0157.
I now calculating, sir.
That is wrong thing. As far as my knowledge goes, that is wrong. Without calculating, you are telling that, okay? So don't think that, okay?
Calculating.
Okay, so everybody is getting how to calculate this. So similarly, you can calculate this. Okay, third value will be this 1.049. Here you write actually alpha. Okay, so here this is beta actually. This is alpha. Again alpha actually. So this alpha varies from 1 to 3. And now overall mixture, viscosity of mixture will be, no, correct actually. That is correct one only. So this will be mole fraction, this divided by this plus this, you can say 0.39 second term, alpha equals to 2. This is alpha equals to 3. So overall viscosity of mixture will be 1714 into 10 raised to minus 7 gram centimeter per second. And everything which we have discussed is a viscosity of gases. Okay, everything we have discussed is true for viscosity of gases. So what we have discussed, just in short, I will summarize. This is what we have discussed. So you should remember this actually forever. So you can get the value of viscosity for gases, pressure and temperature. This is what empirical graph we have discussed. So you can get the viscosity of individual compound or mixture also. You can this here actually it is neglected the interaction for low density of gases. This is true. Again, for low density gases, this kinetic theory gives this equation, Maxwell equation. This Maxwell, you can say kinetic theory equation. Again, this you can use for getting viscosity. And then, if you consider interaction between two molecules and use molecular theory of gases for high density and statistical thermodynamics and molecular dynamics simulation, you get this Maxwell equation where it is collision diameter and collision integral, and this is the how we can get the viscosity of gases per mixture when they are interacting differently actually. So this is what we have discussed. We will continue our discussion in next class actually. If you have any doubt in this, so anyway, we are not discussing the derivation here. So if somebody is very much interested in derivation, I request you to take some molecular dynamics simulation courses. I think it is available online in SWAM platform. You can go in couple of lectures actually. It will take almost 4-5 lectures to understand this actually. So in equations are important. Most importantly, you should know that there are equations available, and this is for gases. Everything is true for gases only. Currently, whatever equation we have covered. So this is true for gases, and this is how we can get the viscosity of gases at different temperature and pressure. This is clear to everybody? Okay, we will continue our discussion in next class. If you have any doubt, you can discuss. Otherwise, you can go and join next class.